the structure and states of matter. In 7th grade, you should have learned what matter was, how matter, anything that has matter, has mass and takes up space. So atoms make up how many atoms in that object is described as the mass. Now, matter is also describing the object not only has mass but takes up space. So the table in my kitchen takes up space of the kitchen. The candle that's sitting on the table takes up space on the table. Now, matter consists of 4 things. We're going to talk about this in a second: atoms, elements, molecules, and compounds. Atoms. You should know that atoms are a pure form of matter. Atoms consist of protons and neutrons. Within a nucleus, protons are the positive. They have a positive charge, while neutrons have no charge or a neutral charge, no charge, and they're in the nucleus, the center. Electrons have a negative charge, and that's very important for the bonding of atoms when you get to chemistry. And electrons are usually flying, they believe, on the outside. Okay? Atoms make up elements. An element could be gold. Gold could have just one atom of gold, and that's the element. Or gold could be thousands and thousands of atoms of gold, making a large chunk of gold sitting in my hand. Both of those are still elements. You can have a single atom of gold, which is an element, or I can have many, many atoms of gold together, making a larger structure, and it's still a pure element. Elements are pure substances made up of one atom or many atoms of that single kind. Okay? If I combine gold with silver, it's no longer an element. It can be a mixture, or it can be, if I have oxygen and hydrogen, it could be a compound or a molecule. Elements are pure forms of matter. They consist of one type of atom, and they're listed on the periodic table. Now, the atomic number and atomic weight, you don't need to know right now. When we go into chemistry, you will need to be aware of that, and we'll talk about those in a future chapter. Molecules. Now, molecules and compounds is where some students have trouble. Molecules can be a combination of elements, same or different. So, what does that mean? If I have 2 oxygen elements, 2 oxygen atoms that combine, okay, forming O2, they bond. That's a molecule. Now, I can also have a water molecule. I can have a hydrogen, an oxygen, and another hydrogen. So 2 hydrogens, 1 oxygen, they combine, they bond. That's a water molecule. So a molecule can be a combination of 2 or more different elements, 2 or more different atoms, or 2 or more similar atoms bonded together chemically. Okay, so O2, 2 O's, that's the same. Or you can have H2O, 2 H's and an O bonded together. They are different. We have H's and O's. That's a molecule. Now, how's that different from a compound? Compounds generally are going to be 2 or more different elements. So you would not have O2 and describe that as a compound. You would say, okay, we have O2, that's a molecule. But if you have H2O, they bond 2 different, that could be a compound, but it can also be described as a molecule. So there's some confusion there, okay, but that's how it goes. Okay, so we can have a water molecule, also known as a water compound, but you wouldn't say you have O2, you wouldn't have O2 compound, it would be an O2 molecule. Okay, mixtures. If molecules and compounds are bonded chemically, mixtures are bonded not chemically, but physically. Mixtures you can separate through a physical means. This could be with my hands, this could be with a hammer. I can separate them physically. But it can also be separated physically through changing of states. When I say that, I mean I can go from liquid to gas. I'm changing a state. It's a state change. So let's say I have salt water. Well, salt water isn't a mixture. Yes, because I can separate that salt from the pure water by evaporation or vaporization. So if I evaporate that water, I vaporize the water off, I'm left with the salt. Well, the water just doesn't disappear. The water is going from liquid to gas. The water is still water, but it's moving around faster in the air. So a mixture, there are 2 types. There could be a homogeneous mixture or a heterogeneous mixture. Homogeneous, homo The prefix homo means same. It looks the same throughout. Hetero means different. Hetero looks, you can identify the different things. So a homogeneous mixture could be salt water. When all the salt is dissolved, and I look at the salt water, it just looks like regular water to me. So the salt water, okay, I can't see the two things. It looks the same, but I can separate them. That's a homogeneous mixture. But if I take this, let's say I have pure water, and I take this thing of salt and I pour it into the water, and I can see this clump of salt. That then would be a heterogeneous mixture because I can see the two different things. I can see the water, I can see the salt. Now, if I dissolve all that salt, then that heterogeneous mixture would then become a homogeneous mixture because it looks the same throughout. Another example of a heterogeneous mixture, a salad. I have tomatoes, lettuce, cucumbers, carrots, and I can pick them out, but I can see them. So that would be a heterogeneous mixture. I can identify the different parts. Now, there are 3 basic states of matter, which you should have learned in 6th grade or 7th grade. Solids have a definite volume and a definite shape. The atoms in a solid are vibrating, but very slowly. A solid, when I said a definite volume, that means the volume does not change. How much space it takes up. So if I have a container of water, and let's say that container of water is 10 milliliters, and I drop a rock in it, that rock goes down, and the water rises from 10 milliliters to 12 milliliters. That means the rock, okay, has a volume of 2 milliliters. That will never change, no matter where the rock is. It always keeps that volume of 2 milliliters. And the rock will always keep its shape when it's a solid, okay? Now, if I have a liquid, okay, let's say liquid water, the molecules are vibrating a little faster. I can move through it. It's not as easy to move through liquid water as it is gas water, okay, like the air. But it's definitely a lot easier to move through liquid water than solid water. Okay, I can't move through solid water, ice. Now, liquid water does have a definite volume no matter what container I put it in. Let's say if it's 10 milliliters of water and I put it in a skinny long tube, it's still going to be 10 milliliters of water. If I put it in a large kind of wide container, it'll look different. Okay, so the shape is changing, but the volume is still 10 milliliters. So liquids will always keep their volume, definite volume, but not a definite shape. So the shape changes depending on the container I'm putting it into. Now gases. Gases, it's very hot. The molecules are moving faster. They're more spread apart. So basically what's happening here is gases don't have a definite volume and they don't have a definite shape. And this is illustrated by if I have a container, let's say a square container, very small container, maybe a 1 milliliter container of a yellow chlorine gas. Well, then I go ahead and put that yellow chlorine gas in a large, maybe 100 milliliter circular container. Well, that dark yellow chlorine gas which was in a little square shape, okay, now it will fill up the whole circular shape. It will fill it all up, 100 milliliters, okay, but it will now, instead of being dark yellow because it's spreading out, it will probably be a very faint yellow, okay, so hopefully that makes sense. It would start in a square container, okay, 1 milliliter, and now I put it in 100 milliliter, it filled that whole 100 milliliter up, okay, and it also changed shape. Okay, let's talk about the properties of matter. Now, there are physical properties that are very important. We're going to kind of skim through that. Physical properties describe how something looks, smells, sounds, tastes. Now, there are chemical properties, but technically not. Whenever you have a chemical property, you can't really observe it because it's going through a chemical change. So chemical properties can't really be observed unless it's going through a change. So technically, whenever we want to talk about a chemical property, well, we're talking about a chemical change. So in the properties of matter, What are we going to really focus on? Physical properties, because we can actually see the physical properties, we can observe them, we can look at them and describe them. Chemical properties we can't, because as soon as we start describing it, it's going through a change. So we're going to talk about that when we go to chemical changes. So let's talk about physical properties. Physical properties are divided into two parts. This is not in many textbooks, but there are size-dependent properties and size-independent properties. Now, this is where it's getting a little confusing. Size-dependent, well, really it's not that confusing. If you think about it, size-dependent means these properties depend on size, or size influences it. It's influenced by size. So mass, volume, and weight. These three things are impacted by size. So if I have 5 grams of sugar, you're going to see a little tiny pile of sugar. But if I have 5 tons of sugar, okay, the mass increased. Well, did the size increase? Yes. 5 tons of sugar is going to be huge. Same thing with volume. If I have 1 milliliter of water, that's tiny. But if I have 100 liters of water, well, the size is now large. So size is being impacted here. More volume, probably more size. In the same way, mass by gravity, the weight of an object. Okay, so mass is still being identified, it's being multiplied by gravity, so it's still influenced by size, so it's still going to be big. Now, size-independent properties, this is very easy, just means size doesn't matter. So you don't have to memorize all these, but just be aware of what it's talking about. So a property that's not impacted by size. Size doesn't really matter here. Okay, one of the easiest examples, go down to the bottom of the list, color. It doesn't matter. Okay, the size here, if I have a red object, does that mean all red objects are small or all red objects are big? No, size doesn't matter. I can have a red apple and I can have a red truck. Different sizes. Size doesn't matter here. Density. Size doesn't matter here. Okay, if something is very dense and sinks, it can be a small object or it can be a big object. But you can have a big object that's not very dense, while a small object is. So density, size doesn't matter. It's not impacted by size. Solubility, the ability to dissolve an object into another substance at a certain temperature. Size doesn't matter. Okay. If I have enough of either one of these, I can dissolve it. Okay. Melting boiling points doesn't matter. The size, if it's at that point, it can start to melt. It can start to boil. Okay, the state of matter. This is one of the easiest ones here. Solid. Are only big things solids? No. Can small things be solids? Yes. And that's the same thing with liquids and gases. Okay, it doesn't matter with size. Also, the ability to attract a magnet, magnetic ability, size doesn't matter. So really there's only 3 size-dependent properties, and all the rest are going to be size independent where size does not matter. So just understand or have a grasp of what it's talking about here. You don't have to memorize it all. I might ask you a couple questions about it to see, do you understand this point? Does size matter? Okay, changes of matter. Now we're talking about the changes. So we're going to talk about physical and chemical changes. Physical changes are changes that alter size, shape, location, or physical state, but not the chemical composition. This is pretty easy if you think about it. If I have a piece of paper and I rip the piece of paper up, it's still paper. If I have an apple and I chop up the apple, it's still an apple. Okay, I'm changing the size, I'm changing maybe the shape, maybe I'm moving it around. While I'm changing the location, it's still an apple. Okay, if I have water, that's why evaporating water, freezing water, it's a physical change, physical, okay? That's why we put in the category of water, salt water, being a mixture, because I can physically change liquid water into gas water by evaporation. Because when it goes to gas water, it's still water. I can't see it. It's floating around in the air because it's moving so fast. but it's still water. That's why I can bring gas water back to liquid water through condensation. Okay, you should know this from elementary school. State changes. You should know what freezing is, what melting is. Now, I will help you if you need some help on this, but you need to know with freezing, when we go liquid to solid, what am I doing? I'm taking away heat energy from that liquid. So if I have liquid water, I put it in the freezer. What's happening is the freezer is very, very cold. That liquid water is warmer than the freezer. So the heat energy is leaving the liquid water, going into the air of the freezer, trying to create homeostasis, trying to create a balance. By doing that, it's then taking the heat out of the liquid water, and the liquid water freezes. And the reason why it can do that is because we have electricity keeping the freezer cold. Now, if I put an ice cube in a cooler, without any electricity, eventually the cooler is going to get warmer throughout the day. But a freezer is run by electricity, so that's going to keep it cold, continually taking the heat away. Now, melting. Melting is when heat enters the object. So heat is entering the ice cube, making it warmer, making the molecules move faster, changing it to liquid. So freezing loses heat energy, melting gains heat energy. Condensation. This is very similar, in what we just talked in the last page, in which condensation, we're going gas to liquid, So the warm air is losing heat energy, Let's say I take a cold can of Pepsi, I place it on the counter. So the can of Pepsi is cold while the air is warm. Heat energy is going to leave the warm air going into the can. So if heat energy is leaving the warm air, well, guess what? The warm air is now going to get colder because heat energy is leaving it. The can is going to get warmer, but the air, which is losing the heat energy, the air is going to get colder. And what's in the air? Gas water. So now the gas water is going to start slowing it down because it's losing heat energy, and it's going to turn into liquid droplets all around the can. That is condensation. Those liquid droplets on the outside of the can, where do they come from? Well, it's water. It was gas water that lost heat energy, turned into liquid water. So it's still water, but it turned from gas to liquid on the outside of the can. The can, the water did not come from the inside of the can. The water did not come from a leak. It came from the air. Does that make sense? Hopefully it does. If it doesn't, have me explain it, or listen to this again, or read the slide. Hopefully it makes sense for you. Vaporization. Basically, this is absorbing heat energy. So the heat energy from the stove is going into the water, causing the molecules, the water molecules to move faster and spread out, and then they go to gas. Now, that's vaporization, liquid to gas. But we generally use the term evaporation. Basically, it's the same thing, except evaporation is vaporization at the surface. Then we have desublimation and sublimation. Desublimation is gas to solid. That's the making of dry ice. It's also called deposition. So in a different resource or different textbook, you might hear deposition. And then sublimation is when you buy dry ice and it goes from solid to gas. It has the little fog machine type of thing. So that's sublimation. Now, you know what dry ice is? Dry ice is solid CO2. Remember, CO2, carbon dioxide, is what you breathe out. That's your waste product in respiration. So that is usually a gas, right? Well, they have frozen that at a very, very cold temperature, that gas, and turned it into a solid. Now, what's crazy is there is no liquid stage. So when you have desublimation, you go from gas to solid, there's no liquid stage. When you put your dry ice, on the table and it kind of vibrates and it has this like little smoke, there's no liquid state. It goes solid to gas. Chemical changes. Chemical changes, that's when you're altering the chemical composition. Remember, physical, it's still water going from liquid to gas. It's still the chemical structure. We might change the shape, that's physical, but with chemical changes, we're totally changing the makeup of the structure. This could be an apple, okay? I cut it, so that's physically, but then I leave it open and it starts to change color. It goes from that white to that yellow color. That is a chemical change. Then it starts to rot and smell. That's a chemical change. Okay, I can't get it back to the normal apple now. Okay, it's completely different now. Burning wood, burning a marshmallow, burning paper. It's a new substance now. It's a chemical reaction. Cooking. Okay, I put eggs, milk, flour together. Okay, I can't get it back. Once I cook it, it becomes a cake. Okay, it's a new chemical thing. Rusting. Rust on the outside of that metal. Okay, that is something new. That's a new chemical structure. Now, when two chemicals react, they may give off heat or a substance on the outside or a gas. That's a sign of a chemical reaction.